Hello viewers, welcome to my channel ITJ Olympiads and AP Physics with Ambarish. And today I have brought an interesting problem from David Morin, chapter on oscillations. This is exercise 4.5 and the same problem is also present in Shashibhushan Tiwari, chapter 12, problem number 58. He has also taken the same problem. And some of my students were facing a difficulty in solving this problem, and that's why I decided to take this up. It's a very nice problem and a lot of interesting physics going on, and we'll see, and I'm sure you'll enjoy the analysis. So let me read out the question right away. A person walks at constant speed v eastward with respect to a turntable that rotates counterclockwise with constant frequency omega. Now this figure was not part of the problem statement, it was in fact part of the solution. So this figure is actually a big hint. So I mean, now you have seen it, you cannot unsee this. But just to give a proper interpretation, I have taken the solution figure here itself, but still you will need to do some more analysis just to understand. So this turntable is rotating, and the observer is moving with respect to turntable always facing eastward. Okay, so as obviously east is an absolute direction, right? So moving east with respect to turntable means what? He's always facing east and trying to run, okay, with respect to the turntable that rotates counterclockwise at constant frequency omega. Supposed to be angular frequency, but that's how it is, this term is used sometimes. So it's rotating with an angular velocity omega. That's what's meant by frequency here. Find the general expression for the person's coordinates with respect to the ground with x direction taken to be eastward. So this direction is x axis, this is also the east direction, and maybe you can call this as y direction. You have to find the coordinates of the person with respect to ground, okay, and this is the coordinate system fixed with respect to ground, x and y. Okay, of course there will be another coordinate system. You can think of another coordinate system attached to the rotating frame, but here he is talking about the position with respect to ground. Initial coordinates of the particle being x naught comma y naught. Also show that I've added this part. Also show that the locus of the person in the turntable frame is a circle, and then find the radius of that circle. So I've added this part to the problem because it's very much related to it. And if you want, you can pause the video here and try out the problem for yourself, and I'll get into the analysis straight away. So let's see. So from ground frame, the velocity of the person is what? See, he is moving with respect to turntable facing eastward with a speed v. But then think about the point that is just under the foot of the person. So since turntable is rotating, that means that point, if it is at a distance r from the origin, then that will have some tangential speed, let's say u, and this u will be equal to omega, right? So that's what I've written. From ground frame, the velocity of the person is superposition of velocity of the person related to turntable, that is small v, and velocity of particle under his feet should have been thanks to my dyslexia or whatever, under his feet, u is equal to omega r. Okay, so this particle is moving with u is equal to omega r. Now let x and y axis with respect to ground be fixed as shown. Then we can write the components of his velocity vectors as, see, this velocity is v and this is u, and this angle is again theta. See, this is theta and this is 90 degrees, so it's again theta, right? Okay, so then what is the rate of change of his what's the x velocity? So this is v and this angle is again theta, so this is u cos theta, and this one is u sin theta. So x direction net velocity in the x direction becomes v minus u sin theta. So that's what I've written. X dot I mean time derivative of x, that is v minus u sin theta. Similarly, what about the rate of change of y coordinate? See, in the y direction, the velocity is only because of this u, and this angle is theta, so this is u cos theta. So y dot is u cos theta. Okay, and u is of course equal to omega r, and x can also be written as r cos theta, and y can be written as r sin theta, as you can see from the figure. Okay, so now if I use this equation 2 in 1, I can write x dot as v minus omega y. Why? Because x dot is v minus u sin theta. But what is sin theta? Sin theta is y by r. So you put that and this by the way, I should have written this as a small r, this is not capital R. Small r and capital R are the same thing. Okay, so if you use that here, sin theta is y by small r and u is omega r, so r will cancel off and you will have x dot as v minus omega y. I'm sure you are able to see it from equation 2. Substitute for sin theta and u as omega r, so that's what you get. So x dot is v minus omega y, and y dot similarly, see, cos theta can be written as what, x by r. So you put x by r and u by r then again becomes omega, so y dot is omega times x. Okay, now what to do with this differential equation? So those of you who are in class 12th or those who have studied the chapter on magnetics, you know that you get a similar kind of differential equation when you are doing cycloidal motion, motion of charged particles in simultaneously electric and magnetic fields. So what do you do? So the same trick I am going to apply here, and I'll be presenting how we are going to do this. So you differentiate it once more. So x dot is v minus omega y. So x double dot is what? Then derivative of v is 0 and this becomes minus omega y dot. And what is omega y dot? See, y dot is omega x. So omega y dot becomes omega square x, right? So because y dot is omega x and you put here, so x double dot then becomes minus omega square x. Now you feel happy after getting this step. This is SHM differential equation. D square x by dt square is minus omega square x. That means what? X coordinate is going to vary simple harmonically, right? And therefore I can write x coordinate as x is equal to a cos omega t plus phi. Okay. And now suppose I use equation 5 in equation 3. So that means y dot is omega times a cos omega t plus phi, right? So y dot is omega and instead of x you put a cos omega t plus phi, and then for y you integrate y dot to get the value of y. So what you will get? You will get integration of cos theta becomes sin theta, so sine of omega t plus phi and plus an arbitrary constant of integration, and when you integrate you will get 1 omega outside in the denominator, and that omega will cancel the omega x, this one omega, and this integration 1 by omega, this 1 by omega will cancel that, and this is what you get for y coordinate. So again be happy, y coordinate will also vary sinusoidally. So and there's some arbitrary constant that we need to see, and we know that here it's a superposition of two mutually perpendicular simple harmonic motions, and so you do expect that it should be some kind of a circle, right? Because again, I mean, you can see that x square plus y minus c whole square is a square, so it will be a circle of radius a. But then so far we have figured out that these are going to be simple harmonic motion, but we still need to evaluate the value of a, phi and c. If I know the value of a, I know the value of phi, and I know the value of c, then I have worked out the entire path of the particle. I know the entire trajectory as a function of time, right? So how do we find a, phi and c? So we need to use the initial conditions. So initially we know that value of x is x naught, and what's the value of velocity? So let me write. So at t equal to 0, x is x naught and x dot is v minus omega y naught. So I've used equation 3, so let me show you equation 3. X dot is v minus omega y. How had we got that? I explained. I had x dot is v minus u sin theta, so sin theta I substituted as y by r, and u I substituted as omega r, and that's how I got x dot is v minus omega y, right? So at t equal to 0, y is y naught, so this becomes omega y naught. So that's what I've written. So at t equal to 0, x is x naught and x dot is v minus omega y naught. So I hope this initial condition is clear, and now I just need to put this in this equation. So put t equal to 0 here, so that means you get x naught is equal to a cos phi. So that's what I've written, x naught is a cos phi, and similarly differentiate this and put x dot as v minus omega y naught. So that's what I've done. So v minus omega y naught becomes minus a omega sin phi. Cos omega t terms becomes omega t terms becomes 0 because t is 0. So 8 and 9, these are the two equations to solve for the unknowns a and phi. So we can easily solve them. Standard technique, we come across this kind of situation so many times in the standard SHM. So if you solve this equation, this can be very easily solved. You get a is this expression x naught square plus y naught minus v by omega square, and tan phi, you just divide this by this and then you'll get the value of tan phi. Tan phi comes out to be y naught minus v by omega whole thing divided by x naught. This you can readily see. Okay, so that is your tan phi, because if you divide sin phi by cos phi, you will readily get tan phi. Okay, so now I have completely worked out the motion of particle in the x direction. So I know a, I know phi, and I know that the motion is a cos omega t plus phi. So x direction we are done. Now I also need to work out the y direction motion. Okay, so what about initial conditions in the y direction? So I know that at t equal to 0, y is y naught and y dot is omega x naught using equation 3. So again, y dot is omega x naught. How had we got that? See, equation 3, y dot was omega x. How did we get this? Because y dot was u cos theta and cos theta was x by r and u was omega r, and so at any instant y dot is omega x. So at t equal to 0, this is omega x naught. So that's what I've written. So at t equal to 0, y is y naught and y dot is omega x naught, and now I'll use this in equation number 6. So what was the equation 6? This one, a sin omega t plus phi plus constant. So this is what I get. I put in the equation 6. So y naught is a sin phi plus constant and omega x naught is a omega cos phi. Okay, so now you can just rearrange this. You already know the value of phi. So using equations 11, this is tan phi, 12 and 13. So you can see, you can take c to this side and you can divide these two equations, then you will get tan phi, and tan phi you can equate from RHS of equation number 11. So here also from 12, 13 you get tan phi, and here you get tan phi, and you equate the tan phi values. So tan phi is from these two equations, tan phi is y naught minus c upon x naught. See, this c will go there and then you divide, omega will cancel, and this is what you get, tan phi. And this tan phi is also equal to y naught minus v by omega divided by x naught. And if you compare these two expressions, you straight away get the value of c as v by omega, right? So I worked out a, I worked out phi, and I worked out c. So everything is known and the complete motion is worked out. So just we'll write the answer in the final form. So x is a cos omega t plus phi, y is a cos omega t plus phi, and plus constant that we just worked out, v by omega, and tan phi, where tan phi is y naught minus v by omega by x naught, and a also we found, x naught square plus y naught minus v by omega whole square. So that's our answer for trajectory as seen from the ground frame. Okay, now if you see, you can easily see that that locus from ground frame is a circle centered at v0 comma v by omega. Why? Because the equation of circle is x minus x naught square plus y minus y naught square is equal to r square, right? Y minus y naught square equal to r square. And if you rearrange this equation, you take v by omega here, so this becomes y minus v by omega whole square, and plus x square becomes a square. So radius is a. Okay, so particle goes in this much radius. Okay, okay. Now the another part of the question was to comment on what kind of trajectory the particle will undergo from the turntable frame. So for this, there's a very beautiful logic that we can apply. Imagine you are sitting on this turntable and you are looking at a far away star in the east direction. Okay, so very far, you are always looking towards the east direction. So what happens from the turntable frame, because your turntable is rotating with omega, for you from the turntable frame, that star will appear to be rotating with omega. Turntable will appear stationary, but that star will appear to rotate with omega. Okay, so that's what I've written. Now imagine looking at a distant star from the turntable frame. This star appears to rotate clockwise with an angular speed omega, because turntable is rotating anti-clockwise, so star appears to turn clockwise. Okay, and since the person always faces this star, he's facing east, that means he's always facing this star. So his velocity vector with respect to turntable must also rotate with constant angular velocity, which is same omega. Okay, so when a star appears here, he is looking here, and when he is turned through some angle, then star goes back, then he is looking here. So his velocity vector, since it's always facing eastern direction, and that means it's always facing the star, and star is rotating with omega from its frame, so velocity vector is rotating with omega, right, constant omega. And when velocity vector is rotating with constant omega, then what is happening? Speed is constant and the velocity is rotating with omega, then it's a case of centripetal acceleration, right? So just like in circular motion also happens, no, velocity vector keeps on rotating with the same omega. So that's kind of thing is happening here. And centripetal acceleration is simply velocity into omega, which is also v square divided by radius of curvature. So if you equate the two, radius of curvature simply comes out to be v by omega. So and this radius of curvature, see, v is constant, omega is constant, that means the particle is going in a path of constant radius of curvature, and that is a circle. Okay, so radius of curvature as seen from the turntable frame is constant, and therefore locus is circle, and this is the radius of curvature. Okay, so this was my analysis of the problem. And if you want some exercise, then you can also try to visualize this motion from the turntable frame and think in terms of forces, what kind of forces will be acting, the pseudo forces and the real forces, and then try to see if you can justify these results from the rotating frame of the turntable also. That will be a very interesting exercise. So this was my analysis for the problem 4.5 from David Morin. I hope you liked this analysis, and if you did like this analysis, please do give a thumbs up to my video, and please share this video as much as possible through WhatsApp groups, Telegram groups, Discord servers, or whatever media you use for networking with your fellow students who are preparing for JEE or Olympiads. And most importantly, if you have not already subscribed to my channel, please do subscribe to my channel, because that's what keeps me motivated to post a new video every day. And thanks a lot for watching this video, and I'll see you in the next one. And as always, God bless you all. Thank you.